Hello, and thank you for joining me. You're here with data science teacher Brandon, and today we have a really fun class. We'll go through all of the ensemble methods and try and determine which is the best ensemble method. Okay. I have a few favorites. I'm always surprised which one works the best, so it's really good to try all of them. Okay. So with this, we're gonna go through the ensemble methods in from the ensemble part for random forest, extra trees, bagging classifier, gradient boosting, and adaboost. We're going to put into the bagging classifier logistic regression, k-neighbors, and the new support vector classifier. We're also going to use the decision tree because a decision tree in a bagging, although is similar to a random forest has a lot of extra randomness involved with that. So it actually does something a little bit different than our bagging with the decision tree. So we're going to try both of those. It's a little bit simpler, but we'll see how they work. Okay, so importing the data. I'm going to go really quick through the pre-processing because it's not really the deal. Today is predicting the spaceship Titanic. This is actually a Kaggle competition, and it's a good hard data set. There's a lot to do in it, so I'm not going to spend a lot of time, but I really wanted a hard data set that was, used for competition prediction was good, and this is one that I had a lot of fun with. So doing some EDA. I'm not going to spend a lot of time on the EDA, and let's go through the pre-processing. So start the pre-processing. Let's go down here. So null values, checking for null values. I'm filling the null values with the most, I'm getting rid of here when there's three null values per row. I didn't want that to kind of mess up prediction. So when there's rows with more than three null values, I'm gonna drop those. Drop those IDs right there. And then I'm going to go fill the NA with the median for these values, cabin zone and cabin code. Okay. Doing a little bit of truncating of the outliers here, and for quite a few different columns here, I'm replacing some of the, or I'm splitting, bucketizing the room service column. I'm going to, just to make it a little bit more sense, changing this exponential distribution into a one hot encoded category eventually, and we'll come to that section. Doing that a few times with a few different ones, and also I made a function to look at these and go through this, and then just replacing some of the last values here in one of the categories with the most commonly occurring value. Okay. And feature engineering, creating one hot encoded categories for when it's 0. I found this to be a good little data set. So when this value is 0, I'm going to make it a 1. I'm going to create another column that represents that as a 1 in case it's more of an event than necessarily a 0 in a continuous variable. So binary for 0, for less than 4 for this other one. So creating kind of, when those things are true, creating a couple of categories for those. Okay, found that to be good. And predicting, below all the stops for this competition prediction. Okay, so we got quite a few features. Lots of these are engineered from this, but doing right after here, the same kind of, it all works the same after here. So train test splits, splitting this, standard scalar, doing that, standardizing my data set right here. Going to do a little function here that's just going to get the, so I'm going to give this a fit model already. I'm going to get the train and test scores and return both. Those make the coding a little bit easier all the way through. Bagging classifier here, logistic regression. Inside of that, I'm going to fit this. Okay, so I get 77 and 76 on the test. 76, so not bad, not amazing or anything like that, but not bad to start. Hopefully we can do better than that though. Okay, so neighbor classifier inside of this, gonna try train this, get 83 and on test 75. So not quite as good, a little bit of overfitting here going on. So we'll go through just looking at the default settings now for the new support classifier. It did a little bit better. It looks like it's doing quite well, and it doesn't have so much overfitting going on, and it was able to achieve both a higher score on the train and test. And we're going to compare all these scores afterwards. Just don't worry, you don't have to remember all these. Decision tree, classic over problem, really overfitting here and getting a not so great score on the test set. Okay, And so we'll do a little bit of hyperparameter tuning, just a very little bit, to see if we can improve each one of these models that doesn't go through. And so we'll go with that. So just trying the default settings and see which one works good. Random forest, a favorite one of mine, but shows some really kind of extreme overfitting going on here. So see if we can fix that. And then same thing for extremely randomized trees. Not quite as good, truly, a little bit worse here. And sometimes I like to use both of these. I'm always kind of surprised, but the extreme trees classifiers is often good, often the best. But sometimes random forest will beat this, and sometimes you're gonna find that this style of model is it either does well or doesn't do well. So adding these different types of mathematics, the decision tree, I guess by itself without the extra random, but the new classifier, the support vector classifier, k neighbors, and logistic regression, you get the benefit of the ensemble method now with the interesting mathematics of each one of these algorithms. Okay. So they should give you a different answer and also benefit from the impact of the ensemble method. So putting all the train and test scores and the names of the models into a dictionary and looking at the dictionary here, starting by the test scores right here. So we actually see the support vector does the best. The one thing I want to just highlight here, the support vector, it takes by far the longest to train when you're doing this in the bagging classifier, many, many multiples of time, longer than any one of the other models. So be aware, this experiment, play around with it, but it does certainly take a long time. So you do get to the point of tuning this and finding it is actually it's many hours to actually go through just the small amount of tuning that we did. So just something to be aware of when you're dealing with this. Mathematics is a little bit more complicated because the decision trees, let's say the other ones are the k neighbors is a little bit more complicated as well, but the decision tree is actually just simple splits and stuff like that. So actually a simpler mathematics, and even the extra trees, which is a really good model, did the worst here, but it has a lot. It's very, very fast to go through any one of these hyperparameter tunings as well. So it could be easier to get to a better score with one of those lower models. But support vector here starts off as our best model with the default settings. And so let's try it, and let's go down from the best model, and let's try gradient boosting next and see which one of these ones we can get the best as we go through these. So I'm just going with the new support vector classifier here. Inside of a bagging classifier, we're going to try the number of estimators here. So to go iterate through this, and really, you see, really, it didn't make a huge difference in the scores. I'm putting the so I'm going to get the scores in our little function that we had, append the scores to the list, put that in a dictionary, and then put this into a data frame, put the dictionary into a data frame, plot this in a heat map, plot that dictionary in a heat, or that data frame in a heat map, and in the title, I'm going to look at the test scores. I'm going to select out the highest test score. I'm just going to round that to 2 decimal places. And from the estimators, I'm going to select out the same position that had the highest test score here for the numpy.argmax, which gives me the index position of the highest occurring value, which allows you to use that because these were iterated through together. I can then use the same index position to select the same position out of the other list. Okay, so going through that. And so we see here, so 50 estimators and 77 test score right here. So looking really caring about the test score here, although really seeing those in proportion, playing around with the kernels and seeing linear, poly, RBF. This is the standard one that was used, and sigmoid. We get here looking at that in a different kernel, and we're just putting inside the new SVC as we just look through this. This is a simple loop and stuff. Just a much less time consuming thing than a full grid search, and you can usually get pretty good just by choosing a few of these and the most important features. Okay, if within reason, it takes so much less time. Okay, and so here looking at this, and we see that the best kernel was the poly. Okay, so poly, we'll try that in the next one here, and the new is essentially how many support vectors are there going to be, right? And so we're looking at the way that I think of this is as the percentage of data points that can be a support vector, right? Because it's using each data point, so we limit that or increase that number so we can essentially create more. It would highlight overfitting. If you did, the more that you do, you're likely to overfit. Kind of like in a tree fully grow versus something simpler where you can only have a couple support vectors or a fraction of the data points be support vectors. You're going to have less chance of overfitting. Okay. And so here, going through this and then trying all of those, same loop and everything like that. And we can see here, we get a 0.6 new and a 7.8 test score. So another 7.8 here, and trying that in the final model, 77.5, so a little bit better. And we'll go through all these. The gradient boosting I didn't spend as much time on. It's just a really good model with the defaults I find. So I tuned here. There's the estimator. Not a big change, but in certain values right here in the best one, 170, we got 78%. So got a little fraction of a percent higher. You know, it's one of those things you don't know. That's not a large enough difference for there to be statistical certainty that you will perform better on, you know, new unseen data out in the real world as you're making decisions. But it, a little bit of improvement here, trying to see what we can do, get the best. But just noticing here that that does not statistically, it's not statistically provable that that will be different on a different train test split. Very likely that that exact number of estimators is going to be less. So it's good to understand which grouping. You can see here right around the 220 to the 2 or 170, there was the best, slightly higher scores than the rest of them. So I do have more confidence here that somewhere in this range would be a good amount of estimators to use on, or I could at least smaller one to try as we're trying to tune this model in the real world and fine tune it for the real world situation. I feel like it might be somewhere in here. So there's one of the values of seeing this grid search this way, so that we're really iterating through and we're seeing how each one of these are impacting the final score. So because if you look at them, really, you can see here, it doesn't change the score that much, right? So understanding that maybe our 10, 20, 30 best combinations in a grid search are all a fraction of a percent better. And so, we have to be aware that couldn't mean that none of those are going to be better in practice. So it's really important to understand that. Okay, trying the gradient, we're getting a 77.6. K neighbors here, trying at the different estimators first for the K neighbors, and kind of basically got the same score for all of these. We're going to try 130 though, fractionally higher, not enough for a different point when rounded. I'm also going to try the number of neighbors here in the K neighbors classifier, the two big things here, and we can see that I did the best with 8 neighbors right here. But again, pretty small fractionally better. Okay, and so you got 77.2 on this one. The adaboost, trying the number of estimators here. This is just an ensemble method, so I don't need to use it inside of a bagger. You could, and it kind of, I don't know, it's almost a little bit too much at that point, really, right? So, and it would start to take quite a long time as well. Okay, so here, trying the number of estimators, and we're going through this, and you can see again, not a huge difference between any one of these, right? But we do see a little bit of improvement around 20 estimators right here. And the simplest is reducing the amount of overfitting that's happening. Okay, and then going through that, and then 76.2. So they all seem to get like the same ceiling, right? When you see models kind of all behaving like this, you know that your data is missing something, maybe in the way that you engineered it, in other things that you could think about what other data you could collect. You really seem to be missing something, right? That none of your models can get past this certain point. So there's just kind of like that wall. And that means you've engineered enough features, you've tried all the models. There's just something that's missing to this piece of the puzzle. Okay, and it feels like kind of like this barrier where everything just can't get past that. Okay, random forest here is looking at this, trying the number of estimators, and another good one in the, and you can see here, not a huge difference either, but 40 was the best score here. Again, marginally better. And trying the number of min sample splits here. This actually had a bigger impact here. It's a good one to kind of let one side of the tree grow. Cost complexity path tuning is really post pruning is how you get that number the best, but min sample splits is a good kind of shortcut way to an easier one to tune in this format. And see here, it does make it not a little bit more than just a fraction of a percent better for the best model here for 26 splits. Okay. And so trying that and then getting 77. So extra trees here, trying the last one here, going through this is the extremely randomized trees, going through the number of estimators, and we can see 20 was the best here, again, fractionally better, and then trying the min sample splits here as well, because it's a good one for this one as well. And again, not quite as good, but really the larger amount of splits, samples before you have to do a split, turned out to be better here, and that's good preventing overfitting. Okay. Although we never really got to where we'd love to see it to know that we absolutely prevented overfitting, but sometimes you can't bring them into alignment. Okay. So after we did the post pruning here, we kind of got gradient boosting and being our best model, which this is one of my favorites, definitely for sure. although all of them have their time where they all shine. They all work the best sometimes. Gradient boosting is often the best here, and we're able to see take a little bit of, not really too much, just tuning the estimators here. And I said, like, the rest of the arguments seem to work well for this one. I find, okay, the defaults seem to work well, but tuning the estimators can make a big difference here. Got gradient boosting, support vector, random forest. They're all, again, very, very close. Logistic, k-neighbors, extra t's, adaboost, and then decision tree by itself. It really, the big difference between using the bagging with a decision tree, which is what it has by default, or the random forest, is that the random forest has a little bit more randomness at which feature it's going to choose when it does the split. The extra trees takes that even farther and then says we're randomly going to decide the decision threshold for this as well. So just kind of, it's all about the split. The bagging with decision trees doesn't really have, considers all features. Then the random forest considers a random sample of the features, and then extra trees considers a random sample of the features with a random decision threshold. Okay, so kind of interesting, very interesting to see these models. Again, they're all very good, right? And you can see the support vector with a bagging model is often a very good model as well. It takes a long time to train though, so just be aware to make sure you have time for the training. But as you can see, lots of good models here, and they all can be the best sometimes. We got them all very, very close fractionally within the same range as each other. And so, as we can see, it depends on your data set which one is going to be the best. And that's why it's always good to try more than one model. I usually try, like, my rule of thumb is like 5 or 6 different models. Okay. Thank you so much for joining me, and I will see you the next time.